These are the guided notes for Chapter 2, Environmental Systems. This chapter is very much an overview of things that you've learned already in biology and chemistry, so we should be able to move through them pretty quickly, and they should be fairly familiar. The opening case study is with Mono Lake, and here's a picture of Mono Lake. It's kind of a neat place in California. It's what's referred to as a terminal lake. So water doesn't leave. It enters and it's highly mineralized. It picks up all kinds of salts and different sediments as it moves its way. And then because it's a terminal lake, it doesn't take those salts anywhere and it deposits them in Mono Lake. So therefore, Mono Lake is saltier than the ocean and no fish can survive there. It has mono brine shrimp and Mono Lake alkali fry. And those eat algae, but they're also eaten by large flocks of migrating birds. LA in 1913 planned to redirect the water, and it did, so that they could harvest more of this fresh water that was going into it. And Owens Lake dried up, which was near Mono Lake. It became the largest source of wind-blown dust, and in 1982 the salinity of the lake doubled and the volume of it halved. In 1994, there was litigation led by the National Audubon Society because the birds were no longer having a food source to stop over and on their migratory trail. And environmentalists also helped fund this litigation. And they got the Los Angeles Department of Water and Power to agree to reduce the amount of diverted water. By 2009, the lake had risen to 2/3 its original height, and the birds returned. In order for this to happen, Los Angeles had to reduce its water consumption, and some of the things that they did was they took grass lawns and they converted it back to native shrubs, and they passed laws to include the installation of low-flow shower heads and low-flow toilets. So this is just your opening case study that goes over all the different parts of an environmental system. And here's a diagram of Mono Lake showing the shoreline as it previous was, the lower shoreline, and what's referred to as the natural level. So Earth is a single interconnected system. This is the largest system that environmental science considers as the Earth, and many important current environmental issues exist on a global scale. So the environmental system is a set of interacting components connected in such a way that a change in one part of the system affects multiple other parts of the system. Examples include interactions between humans, water, plants, animals, and the specific environment. We can look at smaller systems within a larger system, such as on this side. So the fisheries of North Atlantic, to a physiologist, the cod, the fish itself, is the system, whereas to a marine biologist, the predator-prey relationship between two fish species forms a system. For an oceanographer, the system is the ocean and the currents and its effects on fish populations. And a fishery manager is interested in the larger system. So the system is defined by who's doing the studying. All environmental systems consist of matter, and we've learned that matter is anything that occupies space and has mass, and mass is a measure of the amount of matter an object contains. And we know that weight is the force that results from the action of gravity on mass. Mass and weight are different. But since the bulk of environmental science takes place on the Earth, we don't lose a lot of sleep over using the terms mass and weight. Atoms and molecules, if you think back to chemistry, an atom is the smallest particle that can contain the chemical properties of an element, and it's made of protons, neutrons, and electrons, which are positive, neutral, and negative. An element is a substance composed of atoms that cannot be broken down into smaller or simpler components, and they can be in the form of a solid, liquid, or gas. The periodic table lists all the elements currently known. Molecules are particles containing more than one atom, and compounds are molecules that contain more than one element. The atomic number, and this is one of the ones that you should be familiar with, is the number of protons in the nucleus of a particular element. So the atomic number is the top number in the periodic table, and it tells us the number of protons, and it makes it unique for each element. The mass number is the number of protons plus neutrons. It's not found on the periodic table, but it's referred to as the mass number. And then we have isotopes, atoms of the same element that have different numbers of neutrons and therefore different atomic masses. Now, radioactivity is important because we'll look at this when we look at nuclear power. So radioactive decay is the spontaneous release of material from the nucleus of an atom. It emits a great deal of energy that can be captured as heat. This heat can heat water to steam to turn a turbine to generate electricity. Half-life, which we'll continue to look at, is the time it takes for half of the original parent to decay, and allows us to know the length of a particular radioactive element, how long it's dangerous. So uranium-235 decays to form thorium-231. And this is, like I said, half-life. Some undergo radioactive decay that emit harmful radiation, and we can determine the length of time that a radioactive element can be dangerous. And these are some examples of some parents and daughters and how long their half-life is. Chemical bonds, covalent bonds are when electrons are shared. A perfect example of that is methane. And water is also an example of that. So these are bonds formed by sharing electrons, which is different from ionic bonds, which form from transferring electrons from one to another. So sodium chloride is our very typical example of sodium giving one electron away, chlorine gaining electron, and because sodium becomes positive and chlorine becomes negative, they stay near each other. The opposite charged ions are attracted. But when they go into water, they readily dissolve or dissociate. Chemical bonds, hydrogen bonds are another form of bonds. It's a weak chemical bond that forms when hydrogen atoms that are covalently bonded to one atom are attracted to another atom on another molecule. The big concern with hydrogen bonds is water, and water is going to be significant in our whole unit, and it has some very special properties that we'll talk about next. You could do a whole series of lectures just on water and the properties of water. We're going to summarize them and remind us what they are. Water has a whole lot of unique properties. Some are surface tension that results from the cohesion of the water molecules at the surface of the body of water, which means the water is attracted to itself. And cohesion is the ability of water molecules to stick together. We have capillary action, which is the adhesion of water molecules to a surface that is stronger than the cohesion between the molecules, and that's adhesion. Water sticks to other things. So water sticks to itself, water sticks to other substances. It allows things like our water strider to stand on top of the water. Boiling, freezing. It boils at 100 degrees Celsius. It freezes at 0 degrees Celsius. It has a very high heat capacity, which means you can put a lot of heat into water before it changes state. And it helps regulate climates near lakes and oceans. Density of water is greatest at 4 degrees Celsius. And water is also known as the universal solvent. Many substances dissolve well in water because their polar molecules bond easily with other polar molecules. Top is showing the water at 0 degrees. The molecules are further apart, and therefore the ice, solid water, which is ice, floats on top of liquid water. And that's a unique property that helps a lot of aquatic organisms be able to survive. Just in summary with water, properties that are unique include surface tension and capillary action. The hydrogen bonding makes water sticky. Boiling and freezing. It can be a solid, liquid, or gas at Earth's temperature. It has a high heat capacity, so it protects the Earth from wide temperature swings. It's less dense as a solid, ice floats, and it is a good solvent. It dissolves a lot of things because it is polar. Water is also part of the aqueous system that deals with acids, bases, and pH. So an acid is a substance that contributes hydrogen ions to a solution, and the ones that we'll look at are nitric acid and sulfuric acids, which are part of acid rain. Bases are substances that contribute hydroxide ions to a solution. So sodium hydroxide and calcium hydroxide neutralize acidic emissions from power plants. Looking at a pH scale, 7 is neutral, pH above 7 is basic, pH below 7 is acidic, and the water in the Earth's atmosphere, it has a pH of around 5.65, and that's due to the carbon dioxide. The carbon dioxide readily forms carbonic acid, so it's normal for us to have slightly acidic rain. Looking at the conservation of matter, a chemical reaction occurs when atoms separate from the molecules they are part of and recombine with other molecules. The law of conservation of matter says that matter cannot be created or destroyed. It also demonstrates that we cannot easily dispose of hazardous materials because we cannot destroy them. So even though the forest appears to be disappearing here, matter is conserved in the form of water vapor, carbon dioxide, and solid particles. Looking at biological molecules, so we have inorganic compounds, compounds that do not contain carbon. where the carbon is bound to elements other than hydrogen, or organic compounds have a carbon-carbon or carbon-hydrogen bonds. They are the basis of important macromolecules, which we're going to look at on the next slide. Our 4 types of biological molecules are carbohydrates, which are simple sugars that are used for quick energy. They're used by plants and animals. Proteins, which are made of amino acids and used for structural support, energy, storage, internal transport, and defense. Nucleic acids, which is genetic material, are things such as DNA and RNA. And then lipids, which are fats, waxes, and steroids that help make up cell membranes. They don't mix well with water. Cells are the smallest structural and functional component of organisms. A single-celled organism, things like bacteria and some algae, multicellular organisms such as brine shrimp and humans. And then energy is a fundamental component of environmental systems. Energy is the ability to do work, and power is the rate at which work is done. So that's the difference between power and energy. It's important because things like kilowatt is a unit of power, whereas kilowatt hour is a unit of energy. So if we're looking at living systems and energy, they all absorb energy from their surroundings. And we have things such as autotrophs, which make their own food, and heterotrophs, which must consume food. And the sun's energy is a form of electromagnetic radiation. Our basic unit of energy is a joule. And a joule is the amount of energy used when a 1-watt light bulb is turned on for 1 second. There's some other common units of energy on this table: calories, BTUs, and kilowatt hours. We'll be using all of those in conversions this year. And power is the rate at which work is done. So energy equals power times time. Forms of energy: we have potential energy, which is energy that is stored, like water behind a dam. Kinetic energy is the energy of motion, which is like water released from a dam. Chemical energy is the potential stored in chemical bonds, like the energy in food. And temperature is the measure of average kinetic energy of a substance. Looking at the first law of thermodynamics, energy is neither created or destroyed. It'll just change forms. So there's an analogy here with a car. The potential energy is the chemical energy in gasoline, and the outputs, useful energy, the energy that moves the car, but then we also have waste energy, the friction in the engine, friction of the tires on the road, sound energy from the tires on the road. So not all of our energy is used 100%, but it's not created or destroyed. The second law of thermodynamics is that when energy is just transformed, the quantity of energy remains the same, but its ability to do work diminishes. So some energy is lost is heat. Looking at energy efficiency, the ratio of the amount of work that is done to the total amount of energy that is introduced into the system. A traditional fireplace has a low energy efficiency since so much heat can escape through the chimney, but a modern wood stove, which uses much less wood, is much more energy efficient. And then looking at something like calculating energy efficiency, if you're calculating energy being generated by a power plant, they lose approximately 65% of that energy to heat. 35% of it is then passed on to the electrical wires, where 10% of that energy is lost just in transport. And then if you give it to a light bulb, especially an old incandescent light bulb, 95% of that electrical energy went to heat, and only 5% of it went to light. So a light bulb has 1.6% efficiency. Energy quality is the ease with which energy source can be used for work. It includes obtaining and then conversion process. So high energy quality are things like gasoline, which have a lot of energy in them. Low energy quality is things like wood. It'd be hard to have a wood-fired car. And then entropy, all systems move towards randomness rather than towards order. So the randomness is always increasing in the system unless new energy from the outside is added to create order. Energy conversions underlie all ecological processes. So life requires order. This requires continuous energy input, and the form and the amount of energy available determines the types of organisms that can live in a particular environment. We're going to pause here, and we'll pick up with systems analysis in our next video.